Welcome to November Services. In this presentation, we introduce mechanical shock testing, a crucial test that evaluates how well a product withstands sudden impacts, drops, or high acceleration shocks. It simulates real-world events to ensure the mechanical durability and structural integrity of components used in industries like automotive, aerospace, electronics, and battery systems. To understand mechanical shock testing, it is helpful to learn the difference between vibration and shock. To understand mechanical shock testing, it's essential to differentiate it from vibration testing. Shock testing involves applying short, high-intensity acceleration pulses, typically in the range of 30 to 100 grams, to simulate real-world impacts like drops or crashes. It's used to check for sudden structural failures, loose connections, or brittle fractures. In contrast, vibration testing exposes the product to continuous or random motion at lower accelerations over extended periods. Vibration test helps evaluate fatigue behavior, resonance issues, or loosening due to repetitive motion. In short, shock test is used for sudden impact, whereas vibration test used for simulating repetitive motion. Both assess mechanical durability, but they focus on very different failure mechanisms. Importance of mechanical shock test in industries. Mechanical shock testing checks if products can survive sudden impacts like drops or jolts during handling or real-world use. It's critical in sectors like automotive, aerospace, defense, and battery systems to ensure strength, safety, and compliance with standards like IEC 620-68-2-27, MIL Standard 810, and UN 38.3. Mechanical shock testing is widely adopted across industries where safety and durability under sudden impact are critical. From automotive crash protection to aerospace component integrity, these tests ensure reliable performance. Key sectors include EV batteries, defense electronics, consumer devices, rail systems, and even medical or logistics equipment. Now let's take a look at the different types of mechanical shock tests. These tests simulate various real-world impact conditions to ensure that products can withstand shocks during transport, operation, or even extreme events like explosions. Half-sine shock is the most standard test, simulating a smooth, sudden impact like a drop or collision. Trapezoidal shock uses a flat top pulse and is useful when the shock lasts a bit longer, like during transport. Sawtooth shock has a sharp rise and drop and is mainly used in military and aerospace testing. Pyroshock or explosive shock simulates extremely intense events like explosions or missile launches. Drop test freefall shock is exactly what it sounds like, dropping a product onto a hard surface to test durability, especially for consumer goods. The chart on the right visually compares these shock profiles, showing how acceleration changes over time for each type. IEC 6068-2-27 Basic Shock Testing.
This standard is one of the most widely used for mechanical shock testing, especially for electronics and systems. It defines how to apply a controlled single shock pulse to assess structural integrity and performance. The main goal is to check if a product can handle shocks without failure or damage. Some key test parameters include shock pulse types like half-sine, sawtooth or trapezoidal, acceleration levels from 15 G to over 100 G, durations typically between 6 to 30 milliseconds. Usually, 3 shocks are applied in each axis direction X, Y, Z.
To pass the test, the product must not show physical damage, should keep functioning if powered, and must meet all performance limits. This standard is commonly used for automotive ECUs, control units, electronics, and battery enclosures, often alongside vibration testing standards like IEC 600-68-2-6. The images on the right show a typical test setup and an example of a recorded shock profile. AIS 156 Mechanical Shock Test, Battery Safety. This test is specifically designed for EV battery packs and systems to ensure they can withstand sudden mechanical impacts without causing hazardous failures. As shown in the acceleration versus time graphs on the right, the test uses a half-sine pulse with 50 grams acceleration, plus or minus 10%, lasting 11 milliseconds, plus or minus 1 milliseconds. Each battery undergoes 3 shocks per axis, X, Y, and Z, totaling 18 shocks in all directions. Before testing, the battery is fully charged, as per manufacturer specifications, and stabilized at room temperature. To pass, there must be no fire, rupture, leakage, explosion, or unsafe behavior, and the voltage must stay within acceptable limits. This test is mandatory under CMVR regulations in India for all high-voltage EV battery systems to ensure real-world safety and reliability. This test is also for batteries like in AIS 156, as it applies to lithium batteries commonly used in EVs. UN 38.3 focuses on verifying that these batteries can safely endure mechanical shocks during storage and international transport. As shown in the image, the battery, called the DUT, is mounted securely on a shock testing table, which delivers controlled shock pulses. The test uses a half-sine pulse with 150 G peak acceleration and 6 millisecond duration, applying 3 shocks per axis, X, Y, and Z, 18 shocks in total, at room temperature 20 to 25 degrees Celsius. To pass the test, the battery must not catch fire, leak, vent, rupture, or show visible damage, and voltage drop must stay under 10%. This test is quite similar to AIS 156. It uses half-sine pulses, applies 18 shocks across all axes, is done at room temperature, and is meant for EV battery systems. The key difference is in purpose. AIS 156 focuses on safety during vehicle use, while UN 38.3 ensures safety during transport and shipping. In short, AIS 156 focuses on shock survival during vehicle operation, while UN 38.3 ensures safety during transport and handling. Both are essential for ensuring battery safety in different stages of their life cycle. This test is designed to ensure military or ruggedized equipment can survive sudden shocks from handling, transport, drops, or even combat scenarios. There are multiple procedures depending on the application. For example, functional shock during operation.
Transit drop up to 122 centimeters. Crash hazard shock.
And even catapult launch impacts for aviation. The test uses different pulse shapes like half-sine, trapezoidal or sawtooth, with acceleration levels going as high as 100 plus G and pulse durations from 1 millisecond to 30 milliseconds, depending on the equipment's weight and purpose. To pass, the equipment must work properly, especially if it's powered on, and must not suffer any mechanical damage that affects safety or performance. This standard is widely used for military electronics, UAVs, rugged laptops, and is also adopted by aerospace, automotive, and industrial sectors. On the right, you can see a photo of a test setup for a military component, and a graph comparing different shock pulse profiles, half-sine, trapezoidal, and sawtooth, all showing how acceleration changes over time. Finally, the table summarizes the typical shock types used, like half-sine, 11 milliseconds, 40 to 50 grams, for general-purpose testing; trapezoidal, 20 to 30 milliseconds, up to 100 grams, for vehicles or containers; sawtooth, 2 milliseconds, up to 500 grams, for explosive or launch-related tests; drop shock varies depending on drop conditions. This makes MIL Standard 810H one of the most versatile and demanding shock standards used globally. IEC 60068-229. This test evaluates a product's ability to withstand repeated mechanical shocks, called bumps, mimicking vibrations or handling stresses during transport or use. It typically uses a half-sine shock pulse with acceleration levels ranging from 10 to 40 G and pulse durations between 6 to 16 milliseconds. What makes this test unique is the high number of bumps, commonly between 1,000 and 4,000, applied in one or more directions, X, Y, Z. So it's less about surviving one hard hit and more about long-term durability. Compared to IEC 60068-227, which tests single severe shocks, this standard, 229, focuses on moderate repeated shocks, making it ideal for detecting fatigue or loose parts in mechanical assemblies. It's widely used for automotive electronics, battery packs, brackets, sensors, and often paired with vibration and temperature tests. To pass the test, the product must have no physical damage or malfunction and no loosening of connectors or components. On the right, the graph shows the difference between the two standards. 227 in blue delivers one strong shock, while 229 green delivers repeated moderate pulses over time, clearly visualizing their purpose differences. SAE J1455. This test is designed for components used in commercial vehicles like trucks, buses, and trailers. It ensures that electrical and electronic parts can withstand shock in real-world operating conditions, both on-road and off-road. The shock pulse is usually half-sine, with acceleration levels ranging from 10 to 30 grams, and in some cases up to 50 grams, depending on where the component is mounted, like on the cab, axle, or chassis. Pulse durations are typically 6 to 20 milliseconds, and shocks are applied in multiple directions, X, Y, Z, just like other automotive shock tests. This test also considers drop shocks, handling impacts, and can be combined with vibration testing for more realistic scenarios. It's mainly used for chassis-mounted components, engine bay electronics, suspension and frame-mounted devices, including ECUs, sensors, lights, and connectors. To pass the test, the part must show no mechanical failure, function normally within its performance limits, and have no loss of electrical continuity or mounting integrity.
On the right, you can see the typical test setup and the simple shock profile used to evaluate system performance after impact.
Comparison of key mechanical shock test standards. Let's take a quick look at how the major mechanical shock test standards compare across different industries and use cases. IEC 6068-2-27 is one of the most widely used. It applies to electronics, automotive, and industrial products, focusing on single-event shocks like drops or impacts. The test uses half-sine or trapezoidal pulses, with acceleration ranging from 15 to 100 grams. UN 38.3, specifically Test T4, is mandatory for shipping lithium batteries globally. It subjects them to a 150-gram shock over a 6-millisecond duration, ensuring they can withstand transport conditions. AIS 156 is India's standard for EV battery safety. It uses a 50-gram pulse with an 11-millisecond duration, mainly focusing on impact survivability. MIL STD 810 is used for military and aerospace electronics. It allows various pulse types and durations with shock levels reaching 100 grams or more. It's designed to test both operational and survival conditions in harsh environments. SAE J1455 targets truck and bus electronics. It simulates road or cargo-induced shocks with acceleration levels from 10 to 50 grams and pulse durations of 6 to 20 milliseconds. Finally, IEC 60068-229 is for repeated shock or bump testing. It evaluates fatigue and loosening effects from ongoing mechanical agitation with 10 to 40 gram acceleration and pulse durations from 6 to 16 milliseconds. So, each standard addresses a different real-world scenario, from one-time shocks to repeated vibrations, depending on the application. Now that we've seen the different shock testing standards, let me briefly introduce what we offer at November Services in this domain. At November Services, we offer complete mechanical shock testing solutions, backed by expert consultancy to support your product durability validation and compliance requirements. We perform all major shock tests as per global standards, including IEC 6068227, IEC 6068229, UN 38.3 T4, MIL Standard R810, AIS 156 and SAE J1455 using calibrated shock equipment, programmable shock tables and controlled lab setups. Beyond just testing, we help analyze failure modes, recommend mounting or design improvements, and guide component selection to meet real-world shock conditions. Our services support industries like automotive, aerospace, defense, electronics, and battery systems, ensuring your products meet safety, reliability, and compliance goals through both lab testing and engineering consultation. Thank you for your attention. At November Services, we are committed to providing accurate, reliable, and standard-compliant salt spray testing solutions tailored to your needs. If you're looking for testing, technical support, or consultancy, feel free to reach out to us anytime. Stay connected with us for more insights and knowledge at the industry level.